Alrighty, gang, welcome back. Today we are going to talk about, today we're going to talk about polar coordinates. I had intended to post a little bit of a review for you on polar coordinates, just kind of refreshing the stuff from trigonometry. I did not have time to get that done over the weekend, so we're going to start today in section 10.3. Last two sections for this class are 10.3 and 10.4. Just a little quick note, all of those tests that I had to work to get back from the testing center were graded. Did manage to get that done over the weekend. So everybody's test should be in and graded. If you have any questions about that stuff, just reach out to me. You know, the usual channels, Canvas message, email.
Sorry, Professor. Are the 4 extra points because of the GLO worksheet already on or not yet?
I've not put those in yet. So that was another thing I want to talk about today. I appreciate the reminder. I am going to have to set a deadline for that. And I wanted to go in and add them all at once. So the deadline for the Jello worksheet, let me put this stuff in. So here's our title card, which is MAC2312, section 004, which is 2. Today is the 29th of November, 2021. Today, we're talking about polar coordinates. Which is section 10.3. A little announcement. The Jello worksheet is due this Friday at the start of class. So I can't take it after that. We've had quite a bit of time to get this in. It won't take you very long. If you haven't done it yet, please just download the thing, print it, fill it out, and then scan and upload. Remember, you're going to get the points even if you get the questions wrong. So just make sure that you do that as soon as you can. Let's see. Yeah, Zaid, your stuff, I'm still trying to get my hands on physically. I was finally able to get the lady in G25 to dig it up, but I haven't gotten the actual stuff back from her physically. I should be able to get that from her today. Okay, but Jello worksheet, right? Jello worksheet was 4 extra points on exam 2. In order to get those points, I need you to submit that thing no later than this Friday at the start of class. All right. Since we are starting polar coordinates today, we will need Wednesday to finish polar coordinates. I'm starting to lean towards the idea of a take-home test for the last midterm here. I think that will be a relief to most of you, and that will help maybe balance out some of the grades from exam 1. I'm not terribly against it, but academic integrity is of the utmost importance when we do stuff like that. So we'll talk more about it a little bit later. So let's get into the polar coordinate stuff. That's what we want to be spending our time and energy on here today. So we have it. So first, a little sort of review of the polar coordinate stuff that hopefully you saw in your trigonometry class. I know not every trig class does a good job of this. What are polar coordinates? So, polar coordinates are an alternative to Cartesian coordinates, aka XY coordinates, for locating a point in the plane. Right, so the plane, the normal XY plane we're used to graphing things, isn't inherently an XY thing. It is inherently just a flat two-dimensional space. And points in that plane can be determined or located different ways. So the way you're used to thinking of this is the point x comma y, which means you come out here, x along the horizontal axis, you go up here, y along the vertical axis, and that is that ordered pair, right? Like 3 comma 7, you'd come out 1, 2, 3, and up 1, 2, 3, 4, 5, 6, 7, and you're there. Polar coordinates work a little bit differently. Polar coordinates say, go out some distance r along this axis, and then rotate up some amount theta. And that is where you find your point. So it's just two different ways of arriving at this location in the plane. You can tell me how far to go over and then how far to go up. That's the normal Cartesian or XY coordinate. Or I can tell you go out this far and then rotate this amount. And that will get you to that point as well. Where we need to begin is talking about how to go back and forth from one system to the other. So if I give you the equivalent notation for this, we call this the point r comma theta. And the horizontal axis, instead of calling it the x-axis, we call it the polar axis. And this point at the origin here, we call the pole. The first thing we need to do is to be able to go back and forth from one to the other. And the trick to that is thinking about this little right triangle that is created by any point in the plane. So using your basic trigonometry, you can see that the sine of theta is the opposite over the hypotenuse. So that opposite side length there, that would be y. And the hypotenuse there is the radius r. And what this means, if you solve this for y, is that y is equal to r times the sine of theta. And similarly, looking at the cosine of theta, that would be this adjacent side length over this hypotenuse. This adjacent side length is x. So that would mean cos theta is x over r, which means x would be r cos theta. And then finally, thinking about this little triangle again, using the Pythagorean theorem, you know that this squared plus this squared equals this squared. In other words, x squared plus y squared equals r squared. And we usually write that as r squared equals x squared plus y squared. There's one more little sort of rule or identity, if you like, and that's that if you look at the tangent of theta, the tangent of theta is the opposite over the adjacent, which would be y over x. And that will allow you to find theta if you know x and y by thinking usually about the inverse tangent function, but not always. So these are the important tools for going back and forth. This is like your map key for polar coordinates. And the very first thing we need to do is just practice going from Cartesian coordinates of some point to the polar coordinates of that same point. I want to emphasize a few facts here. The first is that while the Cartesian coordinates of a point are unique, every point in the plane has exactly one set of Cartesian coordinates. The point 3, 4 cannot be expressed as any other ordered pair. However, every point has not just one or two, but infinitely many sets of polar coordinates, say representations in polar coordinates. And I'd like you to think for a second about why that is. If I walk out along the polar axis r units and then I rotate up by theta, I could keep rotating, just add 2 pi to that theta. Keep rotating again, add 4 pi to that theta, add 6 pi to that theta, and I'll come back to this same point. There is another sense in which polar coordinates are non-unique, and that has to do with thinking about r as a negative number, right? For any fixed constants x and y, this equation has 2 solutions for r. One is positive and the other one is negative, and we'll need to grapple with those. But while we're here, we can make the restriction or restrictions that r needs to be, say, greater than or equal to 0, and theta needs to be between 0 and 2 pi. And this will yield unique polar coordinates for any point, for a given point. So if I say theta is not allowed to rotate past 2 pi and r can't be negative, then this issue of non-uniqueness goes away. However, for reasons you will see, we don't generally make these restrictions. Right? Oftentimes we will consider r values which are negative, or theta values which are bigger than 2 pi, or negative. And that, you know, is a necessary thing to grapple with in order to do things like graphing functions in polar coordinates. But if you want to force uniqueness, you can, and that's how you get it. So let's take these blue things here and some specific points, x, y, and see if we can come up with the r and the theta. Make sure you have this stuff down, especially the blue stuff in the picture. So let's find polar coordinates for the Cartesian points. Again, Cartesian after René Descartes just means xy coordinates. For the Cartesian points, let's do 1, square root of 3. -1, 1. And what else would be nice? Oh, how about 0, -1? I think at least when you're first starting this, it's always wise to graph the point, just draw the picture. So for A here, the point, the Cartesian point, 1, square root of 3, that would come out 1 along the x-axis, and then square root of 3 is like 1.5-ish. It's a little bigger. That's that point, right? So I know that the x-coordinate is 1, the y-coordinate is root 3. What I'd like to do is find the polar coordinates r, theta. So I can draw this in. This would be theta, and r is this length, which if we think about kind of rotating up from my polar axis would also be this length. The key to finding r and theta are those blue equations from the previous page. So we know that x is r cos theta, y is r sine of theta, r squared is x squared plus y squared, and the tangent of theta is y over x. The top two are useful for going from polar to Cartesian. The bottom two are useful for going from Cartesian to polar. So we're going to use these guys. R squared here is x squared plus y squared. That's 1 squared plus the square root of 3 squared.
Sorry, Professor, did you say that the x r cosine is equal to r cosine theta and y is equal to r sine theta? That's from going to Cartesian to from what? From Cartesians?
Yeah, so here, let me label both of these actually. This is for, we usually use this for going from polar into Cartesian. And we'll usually use this for going from Cartesian into polar. So here I'm giving you the Cartesian coordinates, right? I'm giving you the x and the y, and you need to find the r and the theta. So this one is easy to solve for r. This one is easy to solve for theta. So if we're given the x and the y and we want to find r and theta, in other words, if we're going from Cartesian into polar, we'll usually use these two. And if we're given r and theta and we want to find x and y, that means we want to go from polar to Cartesian, we'll usually use these two. So here in each of these, A, B, and C, I'm given x and y. I want to find r and theta. So for this first guy, 1, root 3, that I've got graphed right here, I need to start by finding r. And I can do that by plugging x and y into this equation. So x is 1 and y is the square root of 3. So r squared equals x squared plus y squared says r squared equals 1 squared plus root 3 squared. 1 squared is 1, root 3 squared is 3. So this says r squared equals 4. And that means r squared equals 4 means that r is one of positive or negative 2. And we could find polar coordinates for this point where r is negative. Let me just choose r equals 2 for now. So I've got my r. I need to also find theta. I need to find this angle that we've rotated up here, right? That looks to me like that's certainly bigger than 0, but smaller than pi over 2, right? It's somewhere between 0 and pi over 2. somewhere between 0 degrees and 90 degrees. The way I find it, I write down the equation tan theta equals y over x, but I plug this in. So tan theta equals √3 over 1. And there's a bunch of ways to solve this. This is definitely something that I am hoping you remember from your trigonometry classes. You could take the inverse tangent of both sides, or you could think about your unit circle. If we take the inverse tangent of both sides, that would mean theta is the inverse tangent of √3. And the inverse tangent of the square root of 3 is pi over 3. Or you could again think about your unit circle. You could ask, where is tangent theta equal to √3 over 1? Well, if you divide top and bottom by 2 here, this would be √3 over 2 divided by 1/2. So where is, sine √3 over 2 and cosine 1/2? That would be at pi over 3. The problem with doing the inverse tangent here, this works fine. You just have to remember that the inverse tangent will only ever spit out angles between negative pi over 2 and pi over 2. So if using arctan, remember that arctan only outputs theta values between negative pi over 2 and positive pi over 2. So if your point was like somewhere over here, where theta is clearly bigger than pi over 2, you would need to do a little bit of critical thinking. What this would actually give you isn't the exact value of theta. It would give you like some, what's the term they use? Like an indexing angle, reference angle, I think is the term they use in trig. So you just have to remember the range of the inverse tangent function is just negative pi over 2 to pi over 2. You can't spit out pi. So sometimes it's easier to get there thinking about the unit circle. Sometimes it's easier to get there using the inverse tangent function. But in either case here, what we have is theta equals pi over 3. Points in the first quadrant are always easy. So the polar coordinates here, and we always write them as r comma theta, r comes first, would be 2 comma pi over 3. If we walk out 1, 2 units and then rotate up by pi over 3, that will get me to this same point. Questions on this first?
When you said that it has infinite amount of infinite representations in polar coordinates, you would just have to add 2 pi over 3, which would give you 7 pi over 3, and then that would be the same coordinate.
Yep. So if we add 2 pi to this, 2 pi is 6 pi over 3. So yeah, 2 comma 7 pi over 3 would get me to the same place. All right, that's saying walk out 2 units and then rotate around 7 pi over 3, which would be like all the way around plus pi over 3. You could also subtract 2 pi. So this could be the polar coordinate 2 comma pi over 3 minus 2 pi, which is pi over 3 minus 6 pi over 3. So that would be negative 5 pi over 3. So that would mean I walk out here and then I go 5 pi over 3, but backwards. That would also get me to this point. So here what I did is I added 2 pi, and here what I did is I subtracted 2 pi. You could also add or subtract 4 pi, 6 pi, 8 pi, any even multiple of pi would do the job. So yeah, and so on, right? There's infinitely many polar representations here. even with the restriction that r is equal to +2. And if you allow me to use -2, I can come up with some more for you. But before we even touch that, I want to get you comfortable with this. So good observation. Any other questions or comments so far? Let's do this again, but for the point -1, 1. And let's try to do it a little bit more quickly. Again, I do think it's worthwhile to graph the thing. So here's the Cartesian point, -1, +1. I'm looking for r and theta. R is this length. Theta is this angle. And we shouldn't have to think terribly hard about this, right? What's the reference angle in here? What's this little angle? If this is -1 and +1, if I've gone out the same amount I've gone up, I'm exactly halfway through quadrant 2. What is this little reference angle in here?
$45.
Very good. It's 45 degrees, or pi/4. So this big angle here would be pi minus pi/4, 3pi/4. I'll write it down. So r squared is always x squared plus y squared, would be -1 squared plus +1 squared, which is 2. So r squared equals 2 means that r is 1 of positive or negative √2. And again, I'll take the positive value.
When we have questions like this, do you care which value we choose, positive or negative?
I will specify. So one common question on my test associated with polar coordinates is, give me 3 representations. Give me 3 different polar coordinates for this same point. And one of them, I will say r needs to be negative. The other 2, I'll say r needs to be positive, something like that. So we'll get there. We're not quite ready for that yet, but yes, I will specify. The other thing we have here is that the tangent of theta is equal to y/x, which is 1/-1, which is -1, i.e. we have tan theta equals -1. Now here's where you can get in trouble using the inverse tangent function. So we might want to say that theta is then the inverse tangent of -1. But what is the inverse tangent of -1? It's not 3pi/4.
Would it be -pi/4?
Yeah. But if I walk out √2 and then rotate -pi/4, that's going to put me down here, not over here. This is why I say you should draw the picture, and you need to think about it a little bit carefully. This is giving you something like a reference angle. But from the picture, we see that theta is actually supposed to be 3pi/4. So theta will always be a solution to the equation tan theta equals y/x. But equations like this have many solutions. The inverse tangent of -1 is just one of those solutions, and it's not the one that we need here. So I hope that we can all see this angle is bigger than pi/2 and smaller than pi. It's a quadrant 2 angle. We need a quadrant 2 angle that gets us exactly halfway through quadrant 2. So that is 3pi/4, something we know from our unit circle. So one possible polar representation here r comma theta would be square root of 2 comma 3 pi over 4. And yeah, you could add multiples of 2 pi, and that would get you to the same point. Or you could subtract multiples of 2 pi, that would get you to the same point. But again, for now, just working on the basics. Let's look at part C. I think we've got room for this one here. C is quite straightforward. I want to get to 0 comma negative 1. So that's this point. Again, r squared is x squared plus y squared. Would be 0 squared plus negative 1 squared, would just be 1. So r is 1 of plus or minus the square root of 1, and we will choose r equals 1. Keep that radius positive for now. If you want to think of theta as being between 0 and 2 pi, then here is theta. What is that angle? That angle that points me due south. Just think unit circle. Very good. Came in a DM. 3 pi over 2. That's the more natural choice. So the polar coordinates r comma theta would be 1 comma 3 pi over 2. If we're keeping r positive and we're keeping theta between 0 and 2 pi, right, to get that uniqueness. We could also use, let's say here's our answer. Right, here's our answer for the last one. We could also use 1 comma negative pi over 2, right? I could say I'm going to walk out 1 and then rotate backwards by pi over 2. So you got choices, right? This is what we mean by non-uniqueness. So I give you a Cartesian point, I could ask you for a bunch of different polar coordinates that get you to that same point. If I gave you the polar coordinates of a point, I could ask you for the Cartesian coordinates as well. That's super duper simple. Find Cartesian coordinates for the polar points r comma theta. I could tell you that the radius is 2 and the say theta is 4 pi over 3. I can tell you that the radius is 1/2 and theta is pi. Let's say negative pi just to keep it fun. But let's do one like this. How about a guy whose radius is -3 and whose theta value is positive pi over 4. And this will be how we introduce the concept of a negative radius. So remember what we said? We said that it's the other kind of duo of map key equations that will let us go from polar to Cartesian. So throughout this, we will use x equals r cos theta and y equals r sine theta. Going from polar to Cartesian really is just a matter of plugging in here. It's very straightforward. So in part A, x is r cos theta, that's 2 times the cosine of 4 pi over 3, which is 2 times what? What is the cosine of 4 pi over 3? These should be quick, quick, quick. Three pi over 3 is pi, so this is pi over 3 past pi. Let me sketch my unit circle. All right, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. All right, 3 pi over 3 is pi. So 4 pi over 3, what's the cosine there?
-1/2.
Very good. So x here is -1. And y is r sine theta. That's 2 times the sine of 4 pi over 3, which is 2 times what? What is the sine of 4 pi over 3?
Square root of 3 over 2. The negative square root of 3 over 2.
Very good. Negative root 3 over 2. And the 2's cancel, and you get negative square root of 3. So the Cartesian coordinates x, y here would be -1 comma negative root 3. All right, really just a matter of plugging things in. We can sketch the point. Suppose I should have done that first. So if we're thinking of sketching it in polar coordinates, I would say, okay, we're going to go out 1, 2 along my polar axis, and then I'm going to rotate around 4 pi over 3, which puts me right here. And the Cartesian coordinates for this point are -1 and negative root 3 over 2. The next guy, r is 1/2, theta is negative pi. Same thing, x is r cos theta, which is 1/2 times the cosine of negative pi. What is the cosine of negative pi? Well, again, thinking about your unit circle.
Is it -1?
Yeah, negative pi means rotating backwards by pi radians. That's going to put me right here. So this is 1/2 times -1, or -1/2. Y is r sine theta, which would be 1/2 times the sine of negative pi, and the sine of any multiple of pi is 0. So this point has Cartesian coordinates -1/2 comma 0. It's right here. And we can think of that as going out, if I mark this as 1, going out +1/2 along my polar axis and rotating around by negative pi. All right, this last one will be kind of fun. Again, we're just plugging in. X is r cos theta. So that's -3 times the cosine of pi over 4. The cosine of pi over 4 is root 2 over 2. So this is -3 times root 2 over 2. Y is r times the sine of theta. So that's -3 times the sine of pi over 4. Sine of pi over 4 is also root 2 over 2. So this is -3 times root 2 over 2 again. Now, just for fun, root 2 over 2 as a decimal is about 0.7. So if you multiply that by -3, the coordinates here are approximately negative 2.12. Negative 2.12. So in other words, this point, and I want to draw this picture and think about it for a minute. Even if we didn't know how to get there in polar coordinates because the radius is negative, we can figure it out by thinking about the thing in Cartesian coordinates. So I'm going to mark this as 1, 2, 1, 2. So where we're going is negative 2.12, or about here, comma, negative 2.12 should be about here. I'll mark this 1, 2, -1, -2, -1, -2. So the XY coordinates of this point put us right here. So if I want to think about this point in polar coordinates, here's your radius, and here's your angle theta. The radius we know is supposed to be -3. So several ways to think about this. You could think about this like, I'm going to walk out +3, rotate up by pi/4, and then reflect through the origin. That's the way I was taught. Let me color this a little bit. The way I was taught to do this is you find the corresponding point with a positive radius, leaving theta alone. This polar point right here would be +3, comma, pi/4. So this pen is dying. And then you reflect that point through the origin, and that will get you the point whose radius is negative, but has the same theta. I think a nicer way to do this, and I don't know why nobody taught me this shit when I was learning it, instead of walking out to the right along your polar axis, walk out to the left. Instead of going out to +3, rotating up, then reflecting through the origin, just walk out to the left, -3, and then rotate by pi/4, because this angle is also pi/4. So a negative radius, you can think of it as doing one of two things. Either you take the point with positive radius and reflect it through the origin, or instead of walking out to the right along your polar axis and rotating, you walk out to the left along your polar axis and then rotate. So if I wanted to find this point using the coordinates that were given, and the coordinates that were given here, remember, write it down, for -3, comma, pi/4, I could say I'm going to walk out -3 along my polar axis and then rotate pi/4 in the positive direction. That will work. That will get you to this point. The alternative is to say I'm going to walk out +3, rotate by pi/4, and then reflect that point through the origin. Now that second way of thinking will be important when we graph functions. Reflecting through the origin when you have a negative radius. But this is, I think, the easier way to begin thinking about it, is instead of walking out along the positive polar axis, walk out along the negative polar axis. Okay, so that's going back and forth from polar to Cartesian. let's get a little more practice with this negative radius business, and then we're going to graph a few very basic functions. Time for fresh paper. Okay. All right, so here's an example of a question that has appeared on several tests of mine. Find 3 polar representations for the Cartesian point points. Actually, let's do 2. We'll do one that's kind of easy, like 0, 2. And we'll do one that's a little harder, like square root of 3, -1. And we'll require that one having a negative value for r. So for each of these xy coordinates, we're going to find 3 sets of polar coordinates, one of which will have to have a negative radius. And for part A here, let's just sketch the point and see what we can come up with. I'm going to just come up here to the regular Cartesian point, 0, 2. There he is. Somebody tell me a set of polar coordinates for this point. And you don't have to think too hard about this. Shouldn't have to write much of anything down. What r and theta will do the job? To get me here. Yeah, very good. If I go out 1, 2, and I rotate up by pi/2, that is the most natural one. That's the one where r is positive and theta is between 0 and 2 pi. All right, so these are polar coordinates, r theta. Okay, can anybody give me another one? Well, the simplest form of non-uniqueness comes from the 2 pi thing, right? So if I say I'm going to just keep spinning until I get back here, that means I still walked out 2. I went pi/2 and then another 2 pi. That's pi/2 plus 4 pi/2 is 5 pi/2. Or you could say I walked out 2 and I rotated -3 pi/2. Anything along these lines will work, adding or subtracting multiples of 2 pi from that original or most natural theta value, pi/2. But what if I want one with a negative radius? So these all have r equal to +2. can we find one r comma theta where r is less than 0, where r is a negative number? Yeah, very good. So imagine I walk out -1, -2, like this. And then I rotate -pi/2. So I go -2 for my r, and then I rotate backwards by pi/2. This will work. And so would going out -2 and rotating around +3 pi/2. And you could find more. All right, so here I've given 5 sets of polar coordinates, which is certainly overkill, 3 of which had a positive radius and 2 of which had a negative radius. And we didn't at any point really need to write down any equations or do any solving. We just need to think about where this point is in the plane, how far it is from the origin, that's your radius, and then where you can rotate from along your polar axis to get there. The most natural one is to say I'm going to go out 2 and then rotate in the positive direction by pi/2. I could say I'm going to go out 2 and rotate in the negative direction 3 pi/2. I could say I'm going to go out 2 and rotate in the positive direction 5 pi/2. Any of those will get me there. Or I could say I'm going to go out -2 and rotate backwards by -pi/2. I'm going to go out -2 and rotate forwards by 3 pi/2. All of these work. You could say I'm going to go out -2 and rotate, what would this be? 3 pi/2 plus 2 pi. 9 pi/2, right? Okay. For B here, I'm going to sketch the graph. I'm going to sketch the point. I'll mark here maybe 1 and 2. I know that the square root of 3 is 1.5-ish, somewhere around there. I'm not sure off the top of my head. Bigger than 1, smaller than 2. 1.7. Okay, so here is root 3. And -1 would be here on my y-axis. So this is the Cartesian point. And I want to find r and theta. And if I'm thinking of theta as being between 0 and 2 pi, the picture is like this. And here we may want to use those key equations. We know r squared is x squared plus y squared. Maybe it's not immediately obvious what r is. And that would be the square root of 3 squared plus -1 squared, which is 3 plus 1 is 4. So r squared equals 4, which means r is again 1 of plus or minus 2. And we know that the tangent of theta has to be equal to y/x. Y here is -1 and x is root 3. So this is -1 over the square root of 3. So I'm looking for angles theta such that the tangent of that angle is -1 over root 3. And one of those we could find by taking the inverse tangent. What is the inverse tangent of -1/√3?
-pi/6.
Good. So one possible theta is the inverse tangent of -1/3. I do not have the iPad here, sweetie, right? That should be in the bedroom. Sorry about that. So one possible theta value here is the inverse tangent of -1/√3, and that's -pi/6. But that's certainly not this angle, right? This big angle that I've drawn here. First off, it's positive. Second, it's way bigger than pi/6. That -pi/6 is this angle. This little guy in here. So polar coordinates for this guy, I could use +2, -pi/6. That will work. If I want to have a positive theta value, what is this big angle here? If this little angle is pi/6 or -pi/6 coming down, what is this big angle here? Well, all the way around would be 2 pi. So it's 2 pi minus pi/6 is 11 pi/6. All right, and we could add or subtract multiples of 2 pi to get more. What about with r less than 0? Well, there's only two possibilities for r. R has to be either +2 or -2. So if I'm going to walk out -2 and spin around to get to this point, what angle am I needing to rotate then?
Five pi/6.
Very good, right? All the way over here to the positive polar axis would be pi. I know that this little reference angle in here is pi/6. So pi minus pi/6 would be 5 pi/6. So there we could, for our polar coordinates r comma theta, use -2 comma positive 5 pi/6. And if we want to get really fancy about it, what angle would I have to rotate here? I want to rotate backwards from this point all the way around to get to here. What is this arc? What is the angle of this big long arc all the way around? It's a little more than pi, right? This would be rotating by pi, or negative pi, because we're going backwards. And then in addition to that, I need to rotate this much more, which I know is pi/6. So this would be pi plus pi/6 is 7 pi/6, all in the negative direction. All right, so there's 4 separate polar coordinates for this guy, 2 of which have a negative radius. This stuff is not too bad, but you do need to practice with it. It will come fairly naturally after you've practiced with it for a little bit. And one of the things we can do to help you start to develop that understanding is to graph some functions in polar coordinates. And that's what we're going to do next. I'm going to start very, very simple. First, though, any questions on how we found these polar coordinates?
No, but
Negative
Professor,
7 pi over 6. Yeah, sorry, just saying this in chat now. Negative 7 pi over 6. I'm thinking I'm going to walk out -2 here because I wanted a negative radius. And then I need to rotate this amount to get to my point. So the point I'm trying to get to is still the same point right here. So the question is, how far are we rotating to travel all the way along this arc to get here? So to rotate from this point to this point is pi, right? In the negative direction. So this would just to go from here to here would be rotating negative pi. And then I know that this little angle in here is pi over 6. So I'm rotating in the negative direction pi and then pi over 6 more. So pi plus pi over 6 is 6 pi over 6 plus 1 pi over 6 is 7 pi over 6. So that's how I would think of it. I'm thinking I'm rotating around by pi and then another pi over 6, and it's in the negative direction. So that's -7 pi over 6. And then did I hear a question coming through voice also?
yeah, I had a quick question. Like you said, this would sort of be the example that we would see on the exam.
Problems like this have shown up on my tests in the past, yes.
And I did have a question on 2 examples back. I was just looking, it was the finding polar for Cartesian points, the C part. It's like, I think 2 examples back.
Yeah, this one?
It was 0 and the points were 0 and -1. No, I believe it was the first example we did.
Okay, let's see, 0 and -1. Yeah. Oh, no, not that. That's, yeah.
Yeah, exactly. I opened up Desmos to sort of get a visual on how the polar points were graphed, and I graphed 1 3 pi over 2, and it does not give the point 0 -1. So I was wondering if there was a way where we could, if there's a specific way you have to put it into like a Desmos program to.
Yeah, that's interesting. I do plan to use Desmos a little bit later, so let's go ahead and do it. You can change Desmos into a polar mode by clicking here and here. And if we ask this to plot the polar point 1, 3 pi over 2, oh, he is putting us somewhere weird. So he's giving me the Cartesian coordinate 1, 3 pi over 2. He's saying this is the x and this is the y. Now, usually this will work. Why is it being silly? Maybe if I type 4, theta equals. Does that do it? No, doesn't like that. Oh. Oh, no, not what we want at all. Yeah, for some reason, he does not want to take polar inputs here. In the past, it used to. I'm not sure why it's not recognizing this is yeah, that's a good question. I'm not too sure. But there is a way to get Desmos to accept polar coordinates that is not this complicated. Let me see if we can find something here. Yeah, well, I know it accepts polar curves really well, which is what pretty much everybody here is doing. But yeah, this person built everything in. So if you wanted, we could do it like within this tool, 1 comma pi over 2, and there we are, right? At the point 0 comma -1 right there. But you have to program for it. So if we wanted to construct something like that, we could. I could say cos theta, sine theta. This would be an ordered pair, and r equals 1. Oh no, won't do that either. Equals. No, doesn't like it. So we got to use different symbols, I guess.
Yeah, I was just curious because I didn't know if it was a problem with the actual work, which I didn't think it made sense, or with Desmos, but apparently it's with Desmos.
Yeah, definitely a problem with Desmos. It doesn't like T either. Okay, let's Q. Q. All right, so here we go. So now we can move my radius around, and we can move my angle around. And if we wanted to type a specific value in here, we could, like 3 pi over 2 and 1. So Q here is your angle, and A here is your radius. I can save this if we want. And send this to you guys in the chat. Oops, sorry, that just went to one person. Okay. All right. Yeah, so if you want to like check your work in Desmos, graphing polar points, you can do this. Just come in here and type what you think is the radius and what you think is the angle, and it will graph that point for you. So for example, if we wanted to try one of the other ones that we're working with, like what was that last guy? -2 comma 7 pi over 6, or -7 pi over 6. And I want to set A to -2. There we go. So you see we are at that point whose Cartesian coordinates were given as square root of 3, -1. Let me see, we hit the same point. Okay. So Desmos being up is good because we are going to talk now about graphing some functions in polar coordinates. I'm going to begin by keeping it very, very simple. Constant functions. These work the same way as graphing functions in Cartesian coordinates. You're going to think of all the ordered pairs r comma theta that satisfy a certain relation. So the graph of a function like r equals r of theta, or theta equals theta of r, is all the polar points r comma theta satisfying the equations. All right, so I can give you r as a function of theta, like r equals cos theta, Or I could give you theta as a function of r, like theta equals 2r. Simplest examples here are like r equals c, where c is a constant. If you don't know what else to do, you can always make a table. So I could have thetas and r's. Usually, it's kind of unfortunate. Usually when we think of graphing, we think of theta as the independent variable. But let's try a few values like 0 and maybe pi over 4, pi over 2, 3 pi over 4, pi. Start there. All right. So r equals c. C is a constant. Then when theta is 0, r is c, whatever that constant value is. When theta is pi over 4, r is still c, whatever that constant value is. When theta is pi over 2, r is still c. When theta is 3 pi over 4, it's always c. This is kind of the polar version of a horizontal line. All right, just for fun, let's assume c is positive. We get the same thing if you assume negative. So the polar point where theta is 0 and r is equal to c would be this point. The polar point where theta is pi over 4 and r is c would be this point. This is c comma 0. This is c comma pi over 4. The polar point where theta is pi over 2 and r is c would be this point, c comma pi over 2. 3 pi over 4 and c would be like here. Pi and c would be like here. And hopefully you see it. If the radius is always c, then you're looking at a circle. This is a circle of radius c, right? This would be the point for 5 pi over 4. This would be c comma 3 pi over 2. And this would be c comma 7 pi over 4. So the graph r equals c, where c is a constant, this is a circle of radius c centered at the origin. And Desmos is good at this. I just give myself a new blank graph and I graph the polar equation r equals 2. It's a circle of radius 2 centered at the origin. R equals 1, it's the unit circle. R equals 5, it's a circle of radius 5. R equals 3 is a circle of radius 3, all centered at the origin. Because these are all the polar points where r is equal to 3, no matter what you use for theta. So no matter how much you rotate, r is always going to be 3. You're always going to be distance 3 from the origin. The next kind of natural one to look at is theta equals a constant. So here you think of r as the variable. You can plug in a bunch of different values for r, like -2, -1, 0, 1, and 2. And theta is always that same constant, c, 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 c. And we can imagine graphing this thing. Again, I have to kind of imagine a particular constant value for theta in order to make this make sense. But if you go out -1, -2, you're going to rotate whatever that fixed constant was. So let me say we're here. If you go out -1, you're going to rotate that same fixed constant. If you go out 0, you're at the origin. If you go out 1, you're going to rotate that same fixed constant. If you go out 2, you're going to rotate that same fixed constant. So if you connect the dots, the polar graphs where theta is just equal to a constant, these are lines through the origin. And this angle you're going to make in here is that angle C. And we can, again, play with Desmos a little bit. Should be good at this. Oh, no, it doesn't like this one. No, won't do it. All right. Yeah, so Desmos only wants to graph things where R is a function of theta, not where theta is a function of R. But these are your constant functions in polar coordinates. And what you notice is that the constant functions, just like in XY coordinates, are the things you use as your references. These concentric circles are constant values for R. And these rays, these lines coming through the origin, those are your constant values for theta. So kind of like your grid in the XY coordinate system is horizontal and vertical lines. Your grid in the polar system is concentric circles and rays emanating from the origin. Next time we are going to start looking at more complicated functions. So I'm not going to make us do any of this right now, but I do want to preview. We'll look at graphs of things like R equals 2 cos 3 theta, or R equals 1 minus sine theta. Sort of the natural things to want to graph in the polar coordinate setting are trig functions, because those functions have the same sort of periodicity that is natural to the polar coordinate system. And they have some nice geometric symmetries. Just for fun, here is 2 cos 3 theta. There's 1 minus sine theta. The green shape here is called a cardioid, because it kind of looks like a heart. And the blue shape here is called a rose graph or petal graph, because it kind of looks like a flower. The rose graphs, petal graphs, there is a nice relationship between the angular frequency, or sorry, angular velocity, the number inside the trig function, and the number of petals. The cardioids can also be modified in interesting ways. If I make this a 2, we'll get a loop. If I make this a 2, then we won't come all the way into the origin. We'll just loop out a little bit. 1.5. So these things all have names, and they're kind of some basic graphs in polar coordinates. In addition to this, I'll show you how to find areas. Bounded by graphs like these. But first, just the graphing. And it turns out graphing the stuff by hand takes a little bit of practice. It's not the most obvious thing in the world. But once we do a few of them, you'll get a feel and you'll be able to do anything. Finding areas in polar coordinates is actually a really nice problem. The other stuff, tangent line stuff in polar coordinates, is not very nice. And the truth is, the way you handle it is by sort of reducing the polar coordinates to parametric equations. And that's not something I'm going to make you do. So the last few topics for us here are just graphing more complicated things and finding areas. Your last midterm, exam 3, I am again leaning towards giving that as a take-home test because we really don't have enough time to prepare between when I finish the lecture material and when the test would be. I could give you the test on Friday. We will be technically ready for it by then, but I think that would be kind of brutal. I want you to have time to work some homework and stuff. So probably test 3 will be a take-home test that I will distribute on Friday. I'll give you very clear rules for how that's going to go. And then your final exam, make sure you have this in your phone calendar. If you do not already, please put this shit in now with like 10 alarms, one at least the day before. It's December 8th at 8 a.m. So it's a weird time. And it's on a Wednesday, right? So it's a week from next class. It's going to be your final. And the final is obviously not going to be a take-home. That will be a proctored test running the same way the rest of our tests have run. It will be in Canvas with Honor Lock and Zoom. That's it from me for today, gang. On Wednesday, we will talk more about polar coordinates, and then we'll finish up the semester on Friday. Hope you guys have a lovely rest of your day. Take care.